Good morning, students. Today we're going to work on Lesson 9, so please turn to page 265 in your student handbook. The questions here are: what information would you need to calculate the volume of each solid? And what is the same and different about how you would find the volume of each solid? Go ahead and hit pause, work through the two questions, go over the answers in a second. So to start here with the cylinder, there's a lot of different options you could pick, but mostly you would need a radius and a height in order to calculate the volume. For the prism, you would need a length, a width, and a height. Other potential answers that you could talk about is you need the area of each base and then the height of each solid to officially calculate the volume. What is the same and different? There's a lot of different options here. One of the things that I wrote down is to find the volume of both solids, you would need to find the area of the base and multiply by the height. What is different? The base on the cylinder is a circle. You would need your radius and the formula pi r squared. For the base on the prism, it has potentially three different options. If this is a rectangular prism, you could consider the base to be the bottom, it could be the left or right side, or it could be the front or back, or even the top. So there are different options, but you definitely need a length, a width, and some form of a height. All right, so let's discuss our ideas here. We talked about the base times the height. Now, when we say base, we have to be really careful here. We have an expression with a capital B, and we would just want to make sure that you're all kind of aware of the notation here. So capital B is referring to the area of the base itself. And when we have a prism, remember the base doesn't always have to mean bottom or top. The base is whatever is congruent throughout the shape. So in a cylinder, we got the same shape top and bottom. If I decide to, I could call this rectangle right here the base. Right? That's the area of the base, and then in that case, the height would be the distance between the bases, kind of like the height is the distance between the two circles. So how could we use the expression B times H for volume? Or what about pi r squared? Well, there's something special about this circle right here. The area of the base is the same as the area of the circle. So in our case here, pi r squared would give us the area of the circle, and we could calculate volume by the area of the base times the height, or more specifically, pi r squared times the height, because pi r squared is the base. So here's our formula for volume of a cylinder. Hopefully you remember seeing that in previous grades. Volume of a prism is the area of the base times the height. In this specific one, if I call the base the length and the width, then it would be the length times the width for the area of the base times the height, which is the distance between the two bases. All right, so our goal here is we're going to analyze cylinder volumes. We're going to look at revisiting the volume of cylinders. What we're going to look at is two different containers. You're going to answer some questions, and we'll have a quick little discussion based off of the outcome. Before we start, just take a look at this. If you need to, press pause on the video. But given the two pieces of information, think about all the different questions, mathematical questions that could be asked. And then keep in mind all measurements are in centimeters. So a couple questions that I came up with quickly is just describe the shape of the base. What is the area of the base? Notice how I used capital B to describe that. Find the volume. What are the units? Find the surface area. What are the units? Compare the areas of the bases. Compare the height of each solid. Compare the volume and the surface area for each solid. So there's a lot of different questions that can be asked just about this context, let's actually explore some specific questions in Activity 9.2 on page 266. So here are two containers. All measurements are measured in centimeters. Your job is to suppose the prism contains water that reaches a height of 1 centimeter. I will note that it says prism, so we're going to refer to the solid here on the right. Draw a representation of the situation, and then look at part B as well. The water is poured from the prism into the cylinder. What is the height of the water in the cylinder? Explain your reasoning. I'll give you a couple minutes to solve this one. Go ahead and hit pause, and when you're ready, we'll go over these solutions. All right, so here's part A. I just drew the situation where we started with 1 centimeter worth of height in the prism, and then I kind of drew that being poured into the cylinder. Now the question then becomes, is if the water is poured into the cylinder, what is the new height that the water will reach in the cylinder? So go ahead and pause the video and work through your explanation on that. So let's take a look. Well, we have all the measurements we know in the prism that we could actually calculate the amount of volume of water that is present. So if we take a look at the prism, we know that the volume of the prism is the area of the base times the height. In this case, our base would be 4 pi times 9, and then we'd multiply that by the height. Well, let's just leave the height as h for right now. So in this case, we get 36 pi for the area of the base, and then we'd multiply it by the height, which is 1. So that tells me right now that I know the volume is 36 pi centimeters cubed. Right? That's how much water we have to go in there. So we know we have 36 pi centimeters cubed. That's how much water is in the cylinder right now. We also know that the cylinder, because it's very similar to a prism, it's got two congruent bases, so the area of the base times the height will give me the volume. But a cylinder is special because the area of its base is a circle, so pi r squared is the area of the base. And we can plug in what we know. So we know that the radius is 6. We do not know the height of the water yet. That's what we're trying to find. But I do know from over here that the volume of water has to be the same as the volume of water in the prism. So that's 36 pi. If I square the radius, I get 36 pi times h equals 36 pi. So if I divide both sides by 36 pi, that leaves the height to be 1 centimeter. So I just figured out right here, we have 1 centimeter for the height. All right, let's turn to page 266 and try number 2. Suppose that the prism contained the water that is reached for a height of 3 centimeters instead of 1. If the water were poured into an empty cylinder, what would the height of the water in the cylinder be? So now we have 3 centimeters worth of water. Go ahead and pause this and work through with whatever logic you want to use. All right, so if we look at the volume of the prism, we knew that that was 36 pi times the height because the area of the base is 36 pi. And we also knew that the cylinder had the exact same area of the base, which means the volume is determined by the height of the solid. If the height is 3 centimeters in the prism, then the height would have to be 3 centimeters in the cylinder as well, because the area of the base is the same for each shape. Therefore, the height would be the same. So in general, whatever the height is of the prism, the water that's in the prism will be the same height for the cylinder. All right, describe what volume formulas you use. Do they apply to just one of the containers or to both? Well, generally speaking, we use the formula, the area of the base times the height. That applies to both. If we want to get more specific, the cylinder we could replace the capital B with the actual area of the base and do pi r squared times the height. How does this formula help explain why the heights were the same for the same volume of water in each container? It all related back to the area of the base. Because the area of the bases were the same, the heights also had to be the same. So, same base area. All right, we're going to do section 9.2 on page 267. If you'd like to pause it right now, go ahead and pause it, read through, and try problems 1 and 2. So let's look at number 1. It says, either sketch or describe in words the three-dimensional solid that would form from rotating around the vertical axis. So here I drew the first one. If the blue shape was rotated vertically around this axis right here, it would kind of look like a two-tiered wedding cake, if you want to think of it like that. I tried to highlight the top pieces of the cake, but you can see that there's basically a cylinder on top of another cylinder. So what would happen if we rotated the rectangle down below around its axis? But notice this rectangle is 3 units away from the axis of rotation. So I would have to first reflect the rectangle over that line and draw a similar triangle. That's a rectangle, actually a congruent rectangle. And then picture that coming up off the page and rotating backwards, and it would create a solid that kind of looks like a roll of toilet paper with a much larger opening or a thinner thickness of toilet paper roll. So now your job is to find the solid's volumes. I'll let you try that. So let's take a look. I want to find the volume of shape A. Well, notice it's 2 cylinders. It's a smaller cylinder on top of a larger cylinder. So what I'm going to do is I'm going to find the volume of the top using pi r squared times the height, and I'll find the volume of the bottom cylinder using pi r squared times the height. Now we do have to be careful because the radius is different for the top cylinder. Here you can see the radius from the center of rotation to the rim is 2 units, and its height is 3. For the bottom one, my radius from the center of rotation, axis of rotation, out 1, 2, 3, 4, 5. I have a radius of 5 for the large circle, and then a height of 3. So radius of 5, height of 3. What I'm going to do is simplify each one of those. So 2 squared is 4, 5 squared is 25, 3 times 4 is 12 pi, 3 times 25 is 75 pi. I actually like to leave my answers as pi. Those are exact answers because there's no rounding when we use pi. So then the total volume is the sum of the top cylinder plus the bottom cylinder. So 12 pi plus 75 pi, which is equal to 87 pi centimeters cubed. If you did that using the pi button, you should have got 273.319 centimeters cubed. If you use 3.14, that's less accurate because you had to round pi, but you should have got something pretty close to 273 point something. All right, so what about the second shape? How do I find the volume of this shape? Well, it's similar to part A because we have 2 cylinders. We have a large outer cylinder and we have a smaller inside cylinder. So what we're going to do is we're actually going to find the volume of the outside cylinder and the volume of the inside cylinder. Notice the exact same formula. Area of the base, pi r squared times the height. For the outside cylinder, we go from the axis of rotation out 1, 2, 3, 4, 5 units. So my radius is 5, my height is 6. Notice the inside cylinder, kind of the one that's hollowed out. That is 1, 2, 3 units because it's 3 units from the axis of rotation. And it has the same height as the other cylinder. So I'll plug in 5 for the outer radius, 6 for the height. For the inside radius it was 3, the height was 6, and we're going to simplify just like we did up above. So we get 5 squared times 6 which is 25 times 6, or 150 pi. 9 squared times 6 is 54 pi. Now here's the trick. Notice, part A, we had a solid on top of a solid. It created a larger solid, so we added the two volumes together. Here, we have a large solid, and we're actually taking away the inside solid. So we're going to actually do the volume of the outside cylinder minus the volume of the inside cylinder, which is 150 pi minus 54 pi. And that gives us 96 pi centimeters cubed, or if you use the pi button, 301.593. If you use 3.14, again, you should be close to the 301. Feel free to pause this, copy the notes down as you need. All right, so let's share our calculations. We kind of already talked about writing your answer in terms of pi, how it's more accurate than using 3.14. But it says, what would happen if the first figure were rotated around the horizontal axis formed by the bottom edge of the figure? So we're going to actually do that here. We're going to rotate around the horizontal axis, which is right here by the bottom edge. And then would the volume be the same with the rotation around the given vertical, the axis? So it wants us to compare the volumes. I'll pause it and show you what we'd come up with. So let's take a look here. What if we rotated around the horizontal axis to the bottom? So I drew that in right to the bottom of the original figure. If it was rotated down, again, it still looks like that two-tiered cake flipped on its side. We got a small cylinder on top, larger cylinder on bottom. The volume, we would find the volume of the top and the volume of the bottom. You can see that they're different radii and different heights. So the volumes do not have to be the same. They could be, but they don't have to be. And here you can see just quickly the volume of these two cylinders give us 99 pi centimeters cubed. If I take the rectangle, rotate it horizontally about the horizontal axis to the bottom side, it would create one, almost like a hockey puck, it would create one cylinder with a radius of 6 and a height of 2. Remember, height is the distance between the bases. So the radius squared times the height would give me 36 times 2, or 72 pi centimeters cubed. So just because we're rotating the same solid but around a different axis doesn't guarantee that the volumes will always be the same. You do have to check those. All right, quick lesson synthesis. Which volumes can be calculated using the idea of today's lesson? Remember, the idea today is volume is the area of the base times the height. So I'll give you a chance to think about that. All right, quick answer. No, this top one, it's a pyramid. Here, the nut and bolt, yes, you could find the, notice how the nut has two bases and a height. Here you would have to do the cylinder part for the screw, the threaded part of the bolt, and then the hex portion would have to be found, but they're both prisms in a sense, so you could do that. Same with the pencil and the stick of butter, both prisms for the most part. The cone, no, that's a pyramid, and the ball is a sphere. We will, in upcoming lessons, learn the volumes of pyramids and spheres, so hold tight. All right, so today I'd like you to annotate the lesson summary for Lesson 9 on page 268 and do the practice problems 1 through 7 for Lesson 9. Remember to check your solutions online, and don't forget about your Delta Math. Have a great day. Adios.